We're gonna talk about power series today. The warm-up I already have on here should be pretty easy. First one, we find it's an indeterminate form. We do L'Hopital, and then we find out through some math and algebra that the answer is 3. Number 2, so the only two places it exists is at -2 and 1. Here it's a vertical asymptote, and here's a cusp corner, whichever you would like to call it. A corner is the technical term, but it is where it is continuous. So that's why this does not work. Then our last one, again, pretty easy. Just doing the derivative, which means we plug this in and then chain roll it, plug in x equals 2, we find 12 over 1 plus ln of 8. Okay, so our notes today, there's a lot of writing today, but power function, we've seen these before in geometry, maybe, and then algebra 2 definitely, and maybe in some other classes you might have seen them, but we've already seen these. Like a parabola is a secondary degree power function, right? We might not call it like that, but that is what it is. So like y equals x squared. And then the parabola's vertex is at A. So we should definitely know that from algebra 2. And we are going to use this word centered at A a lot. We can think of a power function with infinite terms as a power series. Just to be clear, power series are not polynomials since they have infinite terms. They go on forever, but it may help to think of them as infinite polynomials, right? It keeps going on forever and ever and ever. So with this is our infinite series. It is centered at this value A, and then our C of n is going to be some expression that generates a coefficient, some number out front, or some x squared or something like that. Depends on what it is. So some examples of a power series. So I already filled in the information, but I'll explain why I got this. So your C of n is your n right there, and we're starting at 0. And how do I know that? Because this would be x minus 0, and we're lazy, so we're just going to do x. So that's why I know it's 0. The next one, this is it. That's pretty easy to find. And then a equals 1 right there. And our next one is this whole chunk of stuff out here, which we will see a lot. This is definitely something we're going to see a lot. And then we know it's at -3 because it is x minus a. And if it's a +3, it'd be x minus -3. Okay, so what's the point of power series? So power series can be used to approximate other functions. We're going to see it's going to get like really close to, like, this is our parabola here and our sine curve. We're going to use this parabola right here to get really, really close to that and approximate right about like here is kind of where it's going to converge, and then it'll diverge. It'll go away from the original function. Eventually, we're going to learn about different expressions, Taylor and Maclaurin series, and we're going to be able to approximate them about a point, the A value. Diagram at the right shows this. So I guess above. So there it is. Shows that. And then if we were to estimate the value of sine of pi over 3 by calculating the first 4 terms of the power series, so we're just going to plug in pi over 3 for every x value over here. In a calculator, obviously we can do it very quickly. I just used a decimal form for this. And then if we plug it in using the power series, then we have just about, it should be approximately the same answer. It usually will be pretty close, but then we're going to have error bound stuff, which we talked about alternating series error bound, and then we're going to talk about Lagrange error bound. Mixed feelings on that one. Pretty much the same though. Okay, so for now, we're going to be focusing on convergence of a power series and the implications of that convergence. So this first bullet point here, the convergence of a power series depends on the x values, very much like how the geometric depends on our r value. And then note that power series always converges when x equals a, right? So if these are the same, then this would be 0, and it's going to converge to 0. To determine convergence, we're going to use the ratio test. Going to get very familiar with the ratio test. And then we're going to solve for all the values of x that result in the limit being less than 1. And then we're going to have to test the endpoints. This is very important for us to remember. We're not going to have to test them when it's infinity, so not because obviously if it's infinity, then we can't really test the endpoints. So our first example, for what values of x is the series n factorial x of n convergent? So I'm going to do the ratio test. Nice and easy. We have n plus 1 factorial and then x to the n plus 1. And then the bottom is our original. And we should be able to recognize at this point the things that match. But if you don't, I'll just do it real quick. N plus 1, n factorial. So I'm just spacing out the factorial a little bit. Then x of n times x, n factorial, x of n. And we are going to cancel the things that match and then take the limit. So if we see here, we have the limit of n plus 1 times x. And if we take the limit as n approaches infinity, this right here is going to go to infinity. So we could say it's less than 1 because that's where it converges. But for us, the only place it can really do is to 0. So what that means, the x value has to equal 0. So that might be a little confusing. It's like, wait, I thought it was infinity. So we're trying to find where it does converge, which means it has to be less than 1. So what we're kind of saying is here, it has to be 0 because 0 times infinity. I know that's an indeterminate form for us, but let's just say for the moment, infinity times 0 is going to equal 0, which is less than 1. So that's why it has to equal 0. We're going to see a lot of the opposite here where x is going to be the infinity part because this can be anything. This could be 1,000,000 or it could be 100, whatever it is. Going to infinity but times 0 will mean that's where it converges. So it can only converge at one singular point. And let's do example 2. For a series of x, values of x is a series, x minus 3 to the n power over n convergent. Again, we're going to do the limit. N approaches infinity. We're going to do the ratio test. We're going to get very good at doing the ratio test. And so I know because I've been doing a lot of these that when we're going to cancel some things, this not this one, that n and this one is going to cancel, but we're going to have, let me just write it up here so I can not skip any steps. We're going to cancel this and this, so we're going to have an x plus 3 left on top. So now we have n x plus 3 and then n plus 1. And we should recognize that if we're taking n to infinity, this right here is going to go to 1. And now we're going to have just the absolute value of x plus 3. Oops. There. So now we need to split it up because it's an absolute value. So we need to test both sides if it's plus or minus. So we have x plus 3 is less than 1. And then we have negative x plus 3 less than 1. Nice and easy for this one. X is less than negative 2. And with some math, distribute plus 3. X is going to be greater than 2. Wait, did I? Okay, there we go. Oh my goodness, you know what? It's a minus 3, isn't it? Oops. See, that's why we check will work. Okay. X minus 3 less than 1, so it's x is less than 4. This one will be x is greater than 2. Okay, so just watch your math, I guess. That's why you gotta check, right? It didn't look right, so checked it again. Okay, so now we have 2 and 4 as my interval, but we have to check the endpoints. So we're going to test the endpoints. We're going to plug this back into our function. So our first one, we have x equals 2. And I already plugged in the x equals 2. Remember, you're plugging in for x and not n. I have made that mistake where you get a little like, oh, I see a variable, plug it in. Just make sure you are doing it correctly. And then when we simplify this, we should see that is an alternating harmonic series. So this is going to be convergent by alternating series test. So that one means it's included. So now it's included. So we have hard bracket 2. If you also want to do 2 less than or equal to x, that is also fine. And now let's test 4. So this one on top is going to be 4 minus 3. And it's going to be a positive 1. So we can get rid of that. So it's just going to be 1 over n, which we know is a divergent harmonic series. So this will not be included. Soft bracket or just that. And there we go. And we will test our radiance of convergence. So I'm going to scroll down a little bit here. We haven't talked about it yet, but the radius is basically just split the difference. Obviously between 2 and 4 is 2, 2 divided by 1. So it would just be our radius equals 1. So that's what it's going to look like. Again, it'd be 2 plus 1. Difference between one either direction. Nothing too crazy, so don't worry about that too much. It's pretty easy. And then we have our final answer. It looks like kind of like this. For this one, we do have an absolute value on one side. So absolute of 2, 4, and this is what I mean by the radius of convergence. So it's at 3, right? Because we centered it around 3. And we have the difference of 1 on either side. So our radius equals 1. So this is where it's going to converge. And over here is going to be where it diverges. So this is where it kind of connects with the graph, whatever the graph is, and then goes away from the graph on the outsides. So that's kind of the disconnect. Example 3, I want you guys to do this one, so try this one yourself. Try number 3 and 4, just get into it a little bit, because this next one's going to be a little bit long, but I want you to try it by yourself, and then I'll jump into it here in a second. So pause the video. So you should have tried it yourself. Let's do example 3. Again, do the ratio test. And once we start doing these, we get really good at recognizing the lovely things that are going to cancel. And I'm being a little presumptuous that you understand this. I'll write this here just so you know why I'm canceling this. We can split it by exponent rules. Make sure you do know that. Actually, just gonna have to be very careful. There we go. So that's what I mean by you're gonna have to just start making these connections very fast. So I'm just spreading it out and just getting rid of the things that match. And now we have the limit as n approaches infinity of the absolute value of, let's see, negative 3x square root of n plus 1 divided by n plus 2. And we know sometimes on my notes, I do split it out. So I am going to put this negative 3x out front. And why is that? Because it really doesn't matter for this limit, because the limit only affects the n value. So as n approaches infinity of the absolute value of these square root of n plus 1 and n plus 2, this is going to affect itself. So that's why I'm kind of splitting it off. So this right here is going to go to 1, which is great for us. And we know that's going to be less than 1 to be on the interval of convergence. That's where it converges for the ratio test. So when we do that, I'm going to have the absolute value of negative 3x, and that's just going to be positive 3x. So I'm just going to do 3x. Because it's going to be the absolute value inside. Then we're going to split this off a little bit just to test. So we have 3x less than 1, negative 3x less than 1. X is greater than negative 1/3. So now we have our interval. And now we have to test our endpoints. So we're going to test our endpoints. So we're going to set x equal to negative 1/3, 1/3. Remember, it's just the x value. Oh, x 0. Okay, and then with this one, let me just zoom in real quick. So we know that we're going to do some weird math, and you're probably not going to like it, but we can combine these bases because they share this. Well, multiply, combine them. So some weird math rules. And so negative 3 times negative 1/3 is going to be positive 1. So 1 to the n power doesn't really make a difference. I'll keep it up there just for fun. And then we have n plus 1. And we know that this, if we compare it to the limit comparison test to a p-series, we know it's going to reduce to 1/2 for n to the 1/2. So diverges. I'm going to scooch this step over, give myself some more room. I'm going to do limit comparison test as LCT with p-series because p equals 1/2. And again, this is just my shortcut because if you want to do the limit comparison test for practice, go ahead. But I'm just recognizing it very quickly so we can get through this. And then my second endpoint is positive 1/3. Again, I'm going to have the same idea, but this one is going to have an alternating. So we have -3 to the n, and then 1/3 to the n. And then you right now on a separate sheet of paper, so you should test this yourself. I'm going to just give you the answer, but you should do this because the answer is going to be convergent by alternating series test. So the interval is going to be -1/3, 1/3 with a hard bracket, or if you want to do. And the radius of convergence is going to be 1/3. So make sure you know how to do these parts. I'm just skipping ahead because it's going to take me too long to do it. So you should do it yourself and then check that you got the same answer that I got. Example 4, find the radius and interval of convergence. This one's going to be pretty nice. Ratio test of x to the n plus 1, n plus 1 factorial, then times the original inverted. And I'll write it out just because this one's a little bit faster. Again, I do kind of skip the step of the first thing. Expand. Of putting it divided by each other, just because again, I've done a lot of these, so at this point I kind of know what it's going to look like, and you can write it out. You are more than welcome to write it out, but if you want to keep writing it out, that's fine. To your math. So I just simplified it again, very easy. N plus 1 over x. Okay, so this is what I was talking about earlier. Kind of separating out the x values from the n. So if I separate the x, the absolute value of x is going to kind of just be by itself because the limit as n approaches infinity of 1 over n plus 1, which is going to go to infinity, is going to go for the entire limit to 0. This is going to go towards 0. So now when we have it less than 1, just like the one we did earlier where we said, well, okay, if the x value and all this stuff goes to infinity, then this x will go to 0. So the opposite is true. So if this is going to 0, this x can be any number like infinity. So x is going to go to infinity. Let's say interval. And the radius is also going to be infinity. So you're going to have to think about it like a little bit logically of if we have something approaching 0, which is getting infinitely small, then we can basically multiply it by any number we want on the entire spectrum, and it's going to fit. And then our radius is also infinity because we don't have actual intervals. So it's just a summary of what we just did. There are three possibilities. So example one is when x equals a, x, the one we just did, where it's converging for all, and then when it has an actual number, which is 2 and 3. Okay, so recall that geometric series are the only type of series for which we can calculate the sum. The equation for the sum is the key to this entire lesson that we're doing for this part. So here's just some notes for you to write, just a reminder of what the R value is going to be less than 1 for convergent and all that stuff. So our first one we got here is when a equals 1 and r equals x, right? If our radius, our value is going to be x, we're going to have summation of 1 over 1 minus x, where x is less than 1. Needs to be memorized. That's why it's right there. We're definitely going to see this a lot in the next couple of days. So our goal in this section is to rewrite certain functions as power series using the above equation as a sort of template. The function you are given can be thought as a sum, and you will work backwards to find the equivalent power series. You're definitely going to see this. I've seen it a few times on FRQs. FRQs. So we're going to have to do some manipulation. So this first one's pretty easy. We have 2, and I'm going to do 1 minus x is going to be equal to our a, 1 minus r. So my a value equals 2. My r value equals x. And I'm going to use that geometric series so my a value is 2, and then it's going to be x to the n. Why is it x to the n? Because of what our memorization. So that. You can also write, so that's your answer, sorry. Or you can write, if you notice I did n equals 0, you can also do n equals 1 to x to the n minus 1. These are both the same thing, just a different starting point, right? So not that big of a difference. Okay, example 6, express the following function as the sum of the power series and find the interval of convergence. So kind of a thing of what we just did. So when we have 1 over 1 minus negative x squared, because what I want to find is my r value. And with that, I'm going to plug that back into my formula. Remember, my formula is 1 over 1 minus x. Right, so when my x value changes, then this is going to change. So that's why it's in parentheses right there. Okay, so we want to find where it converges, right? And we know that geometric series has to be the absolute value of whatever that r value is less than 1. So I'm going to take the absolute value of that. And then we have x squared minus 1 is, well, I mean, equal to 0. Then we have x plus 1, x minus 1. Obviously, we're just square rooting both sides. And then we have our interval, which is from -1 to 1. Okay, so again, remember, this has to be less than 1. The absolute value has to be less than 1 for it to be convergent. That's why we're doing the less than 1 and solving for our x value. So if you're ever confused, kind of think about that's why, because it's a geometric series. Less than 1 means it's convergent. So we use the ratio test to find the interval convergence for the other ones. We could have done this in example 6, but the geometric test was so much easier, way easier. And we don't need to check the endpoints because geometric series tells us it diverges at r equal, the absolute value of r equals 1. Remember, in our sheet, it says the absolute value of r greater than or equal to 1 diverges for geometric. So that's why we don't have to test it. Also, unlike the ratio test, the geometric series is not inconclusive, so the endpoints will never be included when we use it. So what exactly does the interval of convergence represent? It represents the x values where the series converges. So kind of what I have here is between -1 and 1 is where it lines up really well with the function that we have and then diverges. So this is a convergent side and these both sides diverge. So this is just kind of a visual representation of convergence and the divergence, where obviously it goes two different directions. You can use the link. I won't be able to because it won't work, but you are more than welcome to plug that in and all that lovely stuff. Okay, example 7. Find a power series representation for the function 1 divided by x plus 2 and find the interval of convergence. So we have 1 over x plus 2, and I'm going to make that look like my 1 over 1 minus x. So I'm just doing some algebra. What I'm doing here is I'm getting rid of the 2. And I'm going to pull up top. Then we have my a value and my r value. So this is just some math magic. So I'm just manipulating it to get it into the format that I want. So I basically just took it, factored out a 2, and kept going until it looked like my formula that I wanted. Okay, so with that, we're going to plug this into my series. Fantastic. So this is my geometric that we used from the last couple of ones. And then we have my absolute value of -x over 2 is less than 1 because that's where the geometric series converges. And then multiply both sides by 2 and take the absolute value, right? Because it's going to be not a -x anymore. It's going to be a positive x. But we're going to have x is plus or minus 2. So it's going to be -2 x 2 for my interval. Or if you want to do parentheses. And then my radius, that should be pretty easy. It's centered around 0 for this one. And then plus 2 minus 2, my radius is going to be 2. Because think of a radius. Radius is smack dab in the middle. And then we go to how far we can reach on either side. And our last one, find a power series representation for the function of x cubed divided by x plus 2 and find the interval of convergence. So I did this on purpose. Because it's going to look very, very similar, if not exactly the same, to what we just did last one. So this is our last question. And I'm going to plug in what that equaled once we did all that crazy math. And so with this, our x cubed value, this This is new. This does not affect the interval of convergence. So for this one, think of it kind of like a constant, and constants don't really make a difference for us. So good for us, doesn't make a difference, and will still be the same interval of -2 to 2, and our radius will still be